Hello class, welcome to this video on the AP Statistics Lesson 4.8 and 4.9 homework. So this is on the textbook Chapter 4, Lesson 3, the final lesson in the chapter. So number one, it says a recent study by Microsoft in Japan investigated the impacts of moving to a 4-day work week. In the study, they gave all of their employees 100% of their pay to work 80% of their usual hours. Microsoft reported a statistically significant increase in productivity compared to the same time period the previous year. What is the meaning of statistically significant in this context? All right, so when Microsoft says statistically significant, that means that the change in the response was too high to just be based off of chance, right? So in this case, the response was the productivity, right? So what they're saying is for part A is that they mean that the change in productivity was too high to attribute to chance. Okay, so that's what I mean by statistically significant. So for part B, it says using what you know about experiments, what is one way to improve the study? Why would this be challenging for Microsoft? Well, if it says that the impacts of moving to a 4-day work week, right? So in the study, they gave all their employees 100% of their pay to work, 4 days instead of 5 days. And they report an increase in productivity, but compared to what, right? So it'd be easier it says compared to the same time period the previous year, but what they could do is assign half of the employees to work with one treatment and half of the days to the original, not without the treatment, right? To compare the productivity between them. All right, so because right now they're comparing it to the same time period in the previous year, but who knows what kind of things might have changed in the previous year that you can't control for now, right? And so the idea is you want to have a control group for this, right? So they should have a control group for those working a 5-day work week. So they would randomly assign half of employees to a 4-day work week and other half to 5-day work week to better compare productivity. Now, in practice, this is hard to do, right? So this is difficult in practice. And the idea is that, well, if some people are not working five days, then it's going to be unfair for the employees working 5 days, right? And so with the same salary, right? So this is difficult in practice because it will be perceived as unfair for other employees that work for more days with the same pay. Okay, so that's a challenge right there. Okay, so let's look at number 2. According to the pregnancy tracking apps, there are a few predictors for determining a baby's biological sex before the anatomy scan at 20 weeks. But do they actually work? One example is the ring test, where the mother holds a dangling ring attached to a thread or string over the belly. If it swings in a circular motion, it's a girl. If it moves back and forth like a pendulum, it's a boy. Suppose we sampled 100 women who did the ring test prior to giving birth, and 56 of them predicted the sex correctly. Okay. And then it says the simulation was performed under the assumption that someone is just guessing. True percent of correct guess is 50%, right? So it'd be just, they're just guessing, right? 50% chance that it's a boy, 50% chance that they get it right, that it's a girl. For example, the graph shows the results of 200 trials. So we're doing a simulation. We're if we were just guessing, what percent could we get correct, right? So we got for 200 trials, we'll see if it's unlikely whether we could get 56%, right? Because right now, according to the test, they got 56 of them correct out of 100, so that's 56% success, right? We want to see if that's likely due to chance, or if that's statistically significant or not, right? So let's look at the first part. So it says, what does the dot above 61% represent? So we got 61%, this dot right here. Okay, so that means we're doing a simulation here. So for part A, right? In one simulated sample, now this is a sample of 100 women, right? Because we're doing a simulation where we're looking at 100 women and then what percent that we got right? So in one simulated sample of 100 women, 61% correctly predicted the baby's sex by simply guessing. Okay, so that's part A. We want to make sure that we interpret that correctly before we proceed. Now, what percent of the 200 trials resulted in a correct percentage of 56% or more? Okay, so what percent of the trials? So let's do that. So we got, if we count these, right? So we're going to count these. What percent of the 200 trials? We have 200 dots here. And we want 56% or more. So here we're looking at these ones right here. How many of these do we have? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 2, 3, 24. Looks like we got 24 here. That's 56 or more or greater. So that's 24 out of 200. That's 12%. All right, so, and what we want to see is that statistically significant, right? Is it statistically significant to get that much of a guess or more, right? That's eventually what we're doing. So do the results from our sample of 100 women and the simulation provide convincing evidence that the ring test is better at predicting the baby's sex than just guessing? Well, the idea is if we were just guessing, right, then it would be a 12% chance, right? Which is pretty high. So if we were just guessing, we could guess 56% or more. We could get 56% or more success, and that would be a 12% chance of achieving that. That is not very rare, right? For it to be rare, or for it to be more statistically significant, or in this case, it would have to be less than 5%. Right? So, or less than or equal to 5%. That's the cutoff that we tend to use here. So, since 12% is greater than 5%, it could reasonably occur by chance. Okay, so since 12% is greater than 5%, a sample of 56% or more correct is likely to occur by chance, or or I could say it's not likely, but it's reasonable, right? It is reasonable to occur by chance. So there is not enough convincing evidence, okay? To suggest ring test is more effective than guessing. Okay, so in other words, it's not statistically significant, right? Now, if the ring test had, for example, 65% or something like that, or 62%, even 62%, that would be only 3 dots that were 62 or greater. So 3 out of 200, that is, let's see, 3 out of 200, that's 1.5%, right? So that would be statistically significant, right? But here, we just don't have enough evidence here. All right, so part D. What sample results would convince you that the ring test is an effective predictor of a baby's sex, and explain? Okay. If we sampled, for part D, okay. Okay, so the cutoff we said was 5% or less than below 5%, right? So we want it to be below 5%, which means we want the results to be, let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, wait, let's see, 1, 2, 3, 5, 6, 7, 8, 9. So this is 9 right here, right? Now, if we want to be, if we have 10, then 10 dots, that would be 5%, right? We want it to be 9 or less, right? So 9 dots or less, because we want it to be technically below 5%, right? So that would be around the 59% mark. So if we get 59% or more correct guesses, then we're going somewhere. We're going to start to get to more convincing territory, right? All right, so we'll say 59% or more or greater would be convincing. Since this would mean that there would be less than 5%. Or 10 out of 200 trials in the simulation. Okay. So yeah, again, we want less than 5% for it to be statistically significant. That's generally the cutoff. That's a good cutoff. All right, so now for part E, it says if we sampled 500 women, and again, 56% correctly predicted the sex of the baby with the ring test, would we be more convinced or less convinced of the ring test's effectiveness? Okay, so if there were 500 women and we got 56%, we would actually be more convinced. And the reason is because as the sample size increases, then that means the variability goes down. And if the variability goes down, there will be less of a chance that 56% will occur by chance, right? And therefore, we would be more statistically significant. Okay, so for example, if I look at this, simulation, right? This is only for 100 women, But if I change this to 500 women, and then I did trials, then this would likely decrease in variability. So it might look like that rather than more spread out. Right now it's kind of spread out, right? But then if it's less spread out, then there's an even smaller chance that 56% is going to happen. And if there's a really small chance here, it's likely to be less than 5%, right? And that's what we want. We want it to be less than 5%. So increase in sample size means decrease in variability, and decrease in variability means that percentage is less likely to happen. So therefore, we would be more convinced, okay? So I'm going to say there would be more convincing evidence. Since an increased sample size means decreased variability. A decreased variability would make getting 56% less likely. By simply guessing. Okay. All right. So let's look at number 3. A recent study was done to determine if consuming peanut products during infancy could reduce the likelihood of developing a peanut allergy. From age 6 months to 5 years, half of the 600 infants susceptible to allergies who participated in the study were randomly assigned to completely avoid peanuts, and the remaining infants were assigned to consume at least 6 grams of peanut protein weekly. At 5 years of age, the researchers monitored the children while they were consumed peanut products in a controlled environment. 17.3% of the group who completely avoided peanuts had developed a peanut allergy, compared to 3.2% of the group with regular peanut exposure. What type of experiment is described in the scenario? Identify the explanatory variable and the response variable. All right. So it says from age 6 months to 5 years, half of the 600 infants were randomly assigned to completely avoid, and the remaining half were assigned to consume at least 6 grams. That's a completely randomized experiment, okay? Okay. Identify the explanatory variable and the response variable. So here the explanatory variable is the level of peanut exposure and the response variable. The response variable is the development of an allergy. Or allergic response to peanuts. All right. So now let's look at part C. Calculate the difference in percent of children who developed a peanut allergy. So this one was 17.3, this one was 3.2. All right, so 14.1%. A statistical test determined the probability of observing a difference in percentages this large or larger purely by chance is less than 0.01%. Assuming that there is no difference in the development of peanut allergies between the two groups. So assuming that there's no difference in their peanut allergy development, so the groups are roughly equivalent in that sense. Assuming that that's the case, then the chances that there's this amount of a difference is less than 0.01%. Does this probability provide convincing evidence that early and regular exposure to peanut products will reduce the likelihood of developing a peanut allergy? And the answer is yes. This percentage is less than 5%. In fact, it's way less than 5%. Yes, 0.01% is way less than 5%. So these results are too unlikely to occur by chance alone. All right. So that takes care of number 3. Again, it's the idea of statistical significance is what we're looking at. Okay, so let's look at number 4. A recent study was done to determine the effectiveness of different types of exercise on cardiovascular health. 406 adults with high blood pressure were recruited for the study. Subjects were randomly assigned to complete an aerobic exercise program, resistance exercise program, a combination of the two, or no exercise program over a 1-year period. At the end of the 1 year, researchers determined the cardiovascular risk profile for the participants based on several common factors. So identify the treatments. Okay, so here the treatments are pretty easy. There's 4, the aerobic, resistance, combination, or none, right? So we got the treatments are aerobic, resistance, both, a combo, and then none. What is the purpose of including a group who did not complete the exercise program? They served as a control group. To establish a baseline. That's what control groups are for. There's to establish a baseline risk profile. I'm going to say baseline risk profile to compare with the other groups. All right, so now in part C, the researchers determined there was a statistically significant difference in the CVD risk profiles for subjects who completed the aerobic program and the combination program. Combination program compared to the control group. So completed the aerobic and combination compared to control. Explain what this means in the context of this study. So they said that they were statistically significant, which means that the observed differences that we see between aerobic and control and combination and control between those two groups were too large for it to be due to chance. Okay, that's what they mean by the word statistically significant. So the differences and the cardiovascular disease risk profile between aerobic and control and between combination and control are too large to be due to chance alone. So that's what they mean by statistically significant. D, the difference was not statistically significant for the resistance only group compared to the control group. So explain what it means. It's similar to here, is that the difference in CVD risk profile between resistance and control group was not large enough. To be able to rule out chance alone as a possibility. So the differences between them were not large. So it could have just been done due to chance, right? So if one was 1% greater or whatever than the other one, then that could have just been done due to chance variation alone, right? So we weren't able to eliminate chance as a possibility, and therefore, I mean, it's possible that there is a difference, but between resistance and the control, but it's hard to tell because it could have occurred by chance as well. All right. Okay, so number 5. So let me erase this so I can make some more room. Oh, actually, number 5 and number 6 are multiple choice. So it should be fine. I should be able to. I don't have to necessarily write things out. So researchers have developed a liquid repellent intended to keep porcupines from gnawing on wooden bridges in a local park. The researchers will conduct a well-designed experiment to test the effectiveness of the repellent by placing wooden stakes in the ground and randomly assigning them to receive either the repellent or a placebo. Which of the following is true about this experiment? All right, so the experiment cannot provide sufficient evidence that the repellent causes the porcupines to avoid stakes. Only an association can be demonstrated. Now, remember that this experiment we're randomly assigning them. So random assignment to treatment groups is a way to determine cause and effect, right? So it's not just going to be an association that can be demonstrated. It's going to be more than that, right? So the answer is not A. Part B, any non-zero difference in gnawing behavior will provide sufficient evidence that the repellent causes the porcupines to avoid gnawing on the stakes. So, and this is not true, right? Just because there's a difference doesn't mean that there's sufficient evidence. It has to be that the difference is large enough. So there might be like a 1% difference maybe, but is that really large enough to have occurred to rule out chance, right? That's the whole point. So it has to be statistically significant. It can't just be a difference. It has to be a statistically significant difference. So it's not B. C, the experiment cannot be used to show the repellent causes the porcupines to avoid stakes, since the repellent is not being compared to other repellents on the market. So this is incorrect, right? We're saying that the repellent, that to show the repellent causes the porcupines to avoid stakes, we're comparing the repellent, that specific repellent, to a placebo, right? It's not like we're using this to compare it to other repellents. We are trying to see if there's a cause of whether this repellent causes porcupines to avoid the stakes. So this is not correct. The difference in the amounts of gnawing behavior on stakes given the two treatments must be statistically significant. They're already using good language there. The difference must be statistically significant to provide sufficient evidence that the repellent is effective. Yes, that's the answer. Let's look at the next one. All stakes with the repellent would need to have less gnawing than all stakes with the placebo to provide sufficient evidence that the repellent is active. Now, it doesn't have to be all stakes, right? What we're looking for is the percentage difference. So there might be some that would have gnawing in other stakes, but what we're looking for is that is the difference statistically significant. So we're looking at the overall percentage of the experiment. Okay. All right. Okay, so number 6, 40 university undergraduate students will be randomly selected from those expressing interest to attend an online webinar hosted by a famous author. Of the 1,200 undergraduate students who expressed interest, 93 were from the University of Michigan. Of the 40 randomly selected to attend the webinar, 6 were from the University of Michigan. A consulting statistician is concerned that there may have been selection bias in the choosing of the participants. To investigate how likely it is that at least 6 of the 40 students chosen would have been from University of Michigan purely by chance, a statistician ran a simulation. The simulation is described by the following steps. So step 1, locate 93 blue and 1,114 red chips. So altogether, that's 1,207 chips. So they had 93 blue, 1,114 red chips. Okay. The 93 represents those from the University of Michigan. The 1,114 represents the other students from other universities. And then we select 40 chips at random because we're selecting 40 students to attend the webinar. And then we record the number of blue chips in the selection of 40, right? So record how many blue chips there were, which is equivalent to how many Michigan students would have been in the selection of 40. So we do the simulation, we run the simulation, and we get 1,000 trials of the simulation were shown. So we did this 1,000 times, and we see that if we look at the 6 students, at least 6, so 6 or more, right? 6 or more, there's 41 simulations 41 trials where you had 6 students, 6 blue chips, 24 where you had 7, 7 where you have 8, and 2 that you had 9. So in total, we're looking at 6 or more is going to be these numbers: 41. Let me just zoom in on that. 41, 24, 7, and 2 would have occurred by chance. So based on the results of the simulation, is there convincing evidence at the 5% level that selecting at least 6 of the 40 students from the University of Michigan is unlikely? So it says, is there convincing evidence at the 5% level that selecting at least 6 is unlikely to have occurred by chance alone? All right, so here we got, let's add these numbers together, 6 or more, right? We want to see if it's at least 6 would have done by chance. So 6 or greater. So 41 plus 24 plus 7 plus 2. So we got 41, 24, 7, and 2. All right, so we got 5, 12, we got 14 here, 5, and 7. So this is 74 out of 1,000 simulations, right? So that's 7.4% chance. All right, so that's 7.4% chance. That's greater than 5%. So they said at the 5% significance level, right? So that means, so when they say 5% significance, that means that's your cutoff. So if it's greater than that, it's going to be statistically insignificant. If it's less than that, it's going to be statistically significant, right? So right now, this is statistically insignificant. And what that's saying is that this, having 6 or more students in the webinar is reasonable to occur by chance, because it occurs 7.4% chance, which is pretty reasonable because it's greater than our cutoff of 5%. Okay. Now, if it were less than 5%, then it would be unlikely. It would be too unlikely to occur by chance alone, right? And so we could rule out chance in that case. However, this is likely to have occurred. This is reasonable to have occurred by chance alone, so we cannot rule out chance. And so here we're saying, is it unlikely to have occurred by chance alone? And the answer is no, it's not unlikely to have occurred by chance alone. In fact, it's likely to have occurred by chance alone. And so we do not have enough evidence to say that it was unlikely. Okay, so we want to look for one that has that percentage here. This one's saying approximately the third quartile. No. Expected blue chips is closer to 3. No. This distribution is skewed to the right. No, that's not the reason why. Suggests that selecting between 0 and 9 students is likely. No. 7.4% of the time it occurs by chance alone. And so we do not have enough evidence. There you go. So it's got to be E. Okay. This idea of statistical significance is really important, especially as we go into chapter 9 and, you know, when we go into inference. So it's important that you understand this idea of statistical significance. All right, so let's take a look at the 4.9. So this is part 2 of the lesson. So it's still chapter 4, lesson 3, but we'll go ahead and finish that off with the last 7 questions here. So at one time, Spotify had a total of 9,000 employees. The CEO wanted to send a survey to 300 of these employees to measure job satisfaction. Describe a method for taking a simple random sample of 300 employees. So here we have 9,000 employees. So if we use a random number generator, we got to go from 1 to 9,000, and then we need 300 employees. So we generate 300 different numbers between 1 and 9,000, right? So no repeats. Send the survey to each of them corresponding to the numbers generated. So this is a review type question. All right, so we'll go ahead and do that here. So label each employee with a unique number from 1 to 9,000 using random number generator. Generate 300 different numbers between 1 and 9,000. Send the survey to employees corresponding to numbers generated. Okay. What is the purpose of taking a random sample? Again, so random sample, the reason why we do a random sample is that it makes it so that there's a good chance that we would have a sample that is representative of the population of all employees. All right. And remember that the scope of inference is when you do random selection, that helps you generalize conclusions to all employees. All right. So whatever conclusion you end up coming to from that survey or from that survey, you can generalize it to all employees. Okay, to all of your 9,000 employees, because you've taken your population of employees and you've randomly selected them, and so you can generalize the results to the entire population for Spotify, right, of the employees. So part B, we say we can random selection makes samples representative of the population. So our results can be generalized to all of Spotify's employees. So it's important that you look at the scope of inference. That's what this homework is mostly about. What can we infer based on the method that was used? If we have random selection, we can generalize the results to the population. But there are certain things that you cannot, certain things that if you don't do, you cannot infer cause and effect, right? But in this case, we can generalize the results to the population, but not necessarily like a cause and effect kind of thing. All right, so that's something to keep in mind. All right, so number 2. An education research organization wants to conduct a survey of teachers to estimate their average annual salary, identify the population to which the results can be generalized for each of the following samples. So if we do a random sample of 100 teachers in the United States, then we can generalize the results, because it's random, we can generalize the results to all teachers in the US, okay? And that's because we took a random sample of 100 teachers across the United States. Now, if we did a random sample of 100 high school teachers in Michigan, then we can only generalize it to high school teachers in Michigan, right? So specifically high school and specifically Michigan. So far, so good. Easy. Random sample of 100 high school teachers at an education conference. Then if you do it at an education conference, right, then you can only generalize it to the high school teachers at the conference, right? So all high school teachers that were at the conference, right? Notice that we're getting more and more specific here. A voluntary response sample of 100 elementary school teachers in Michigan. So this is interesting. You cannot generalize this result to all elementary school teachers in Michigan. You can only use these results to make generalizations about those teachers in that sample, because you didn't do it randomly. It's not random selection. Random selection enables you to be representative of the population and therefore make conclusions about the population. With a voluntary response sample, it's not going to be representative of the population, and therefore you cannot generalize it to the population. So here, only to those teachers elementary school teachers in the voluntary response sample. Okay, so you can only do that. Now, a convenience sample, again, the same thing. It's not random, so you can only generalize it to those specific teachers, right? So only to those high school teachers in the convenience sample. All right, so this is important, understanding this idea, right? All right, so a recent study revealed that teens who spend the most time on social media, 5+ hours a day, are 40% more likely to report symptoms of depression than those who spend the least amount of time, 1 hour or less. Is the study described an observational study or an experiment? So this is an observational study because you're not telling teens to go on social media a certain amount of times per day. You're just observing that, you're just looking at a correlation. You're looking at the teens that do spend and the teens that don't, and then applying a correlation, right? So here, so this is part A for number 3. Oops. Observational study. Since no treatments were imposed on the teens. This is a somewhat common fear response type question on the AP exam. Is they'll ask you, is an observational study or an experiment? So let's make sure it's important to get this right, to get those points, to get at least this point. So part B, can we conclude that more time spent on social media caused an increase of depression and risk of depression? Now, since it's an observational study, we cannot make this conclusion, right? Because the only way that we can conclude cause and effect is if we had an experiment with random assignment. Okay, it's not just any experiment. We have to have random assignment. So that way we can eliminate confounding variables and things like that would also contribute to depression, right? We can control for that. So no, since we do not have random assignment to treatment groups. So we can't infer cause and effect. So it's important. Random assignment. So random selection enables us to make generalizations about that particular group, about the population where that sample came from. Random assignment helps us to infer cause and effect. Okay, so those are the differences there. All right. So for part C, suppose that 80 teens volunteered to participate in an experiment. Here's the key: volunteered. So that's something we want to keep in mind. But yeah, let's just say we have 80 teens. Describe a process that would randomly assign the 80 teens in the 2 treatment groups. Okay, so here, can we infer cause and effect if we randomly assign these? Yes. However, if they volunteered, can we generalize this to the population? And the answer is no. We cannot generalize these results to the population of teens, right? This age group in general, because we did not randomly select those teens, right? Since those teens came to us, we can do the study to determine cause and effect, but we can't generalize those results to the population. All right, so we can say that there's cause and effect for these teens, for example. All right, so part 3C. So let's describe a process that would randomly assign them. So give each teen a number. There's 80 teens, so give each teen a number, a unique number. We should put in unique number from 1 to 80. Use a random number generator to select. We want 2 treatment groups, so 40 in each group. That's reasonable. To select 40 numbers, or let me put 40 different numbers. Between 1 and 80. So again, no repeats. Assign teens corresponding to these numbers to use social media for 5 hours per day. The remaining 40 will only use it for 1 hour or less per day. Okay. All right, and there you go. So that takes care of number 3. So let me, in order to answer number 4, I'm going to clear out the space for number 3. All right, there you go. So we can go ahead and answer the questions now. A group of researchers used a random sample of 10,317 people in Wisconsin to investigate the connection between volunteering and mortality rates. They found that those people who did not volunteer had mortality rates more than double of those who volunteered, with motivations focused on helping others. What is the explanatory variable and the response variable? Okay, so let's do the explanatory. All right, so the explanatory variable is looking at volunteering, right? If they're volunteer or not. So whether or not they volunteer. And the response variable, we're looking at the mortality rate. All right, so was a random sample used to collect the data? Was random assignment used? Okay, so it says they used a random sample of 10,317 people. So it looks like they did use a random sample. So they did randomization. They did random selection, but they never said anything about assigning them into groups, right? They just said that they found that those people who did not volunteer had higher mortality rates, more than double. So they actually didn't do random assignment, right? So it's not a random assignment experiment that we're doing. So in this case, yes, there were 10,317 randomly selected individuals from Wisconsin, but not randomly selected or randomly assigned to treatment groups. There were no treatments in this case. They were just looking at whether they observing. All right, so what conclusion can be drawn from this study? So now, because there's randomization, whatever results that we get, which is, they said that they found that the mortality rates more than doubled, right? They can generalize this to the population of Wisconsin, right? They can say that for the population of Wisconsin, it's found, right? We can generalize that to Wisconsin, that those who did not volunteer had more than double the mortality rate, right? Now, we can't infer cause and effect. We can't say that that volunteering or lack thereof, or lack of volunteering, caused the double mortality rate, the doubling of their mortality rate, because we do not have treatment groups, right, where we did random assignment. However, we could still say that there's an association for all people in Wisconsin. Okay, so for all people in Wisconsin, there is not a cause and effect, but there is an association. Between whether or not a person volunteers and mortality rates. All right, so number 5, one of the responsibilities of astronauts on the International Space Station is to operate a robotic arm to perform tasks. Researchers wondered if administering a low dose of caffeine and exposing the astronauts to blue-enriched white light would improve the robotic arm task performance. 16 volunteers were randomly assigned, so there's that randomly assigned, to several treatment groups: only caffeine, only white light, both caffeine and white light, or no caffeine or white light. The researchers found that the group with both caffeine and white light had the highest scores for task performance, so both caffeine and white light. Interesting. Okay. What conclusion can be made from the study? Now, in this case, we said that there is a cause and effect because we have random assignment, right? So, but can we infer this to the population? No, because we had volunteers. We had 16 volunteers, so we can only say that for these 16 astronauts, or these 16 volunteers, that there was a cause and effect between getting a low dose of caffeine and exposure to blue-enriched white light, and that causing the robotic arm task arm performance to improve. Okay, so our conclusion. In conclusion, we can say for these 16 astronauts only for these guys, there's a cause and effect here. Getting a low dose, it says the group with both caffeine and white light had the highest scores. So getting a low dose of caffeine and higher exposure to white light caused their robotic arm performance to improve. All right, so let's look at number 6, where we have a couple multiple choice questions. To investigate whether a strenuous exercise regimen would improve the strength of high school wrestlers, a wrestling coach selected at a random sample of 30 wrestlers at Jefferson High School. So we had a random sample, so that's random selection. The wrestlers were randomly assigned, okay, so we got random assignment to one of two treatments, a strenuous exercise regimen and the current exercise regimen for wrestlers. At the end of 5 weeks, the strength of the wrestlers was measured based on the design experiment. Which of the following is the largest population to which the results can be generated? So we can, or generalized. So we can generalize these results. Since we have random selection, we can generalize these results to all of the wrestlers at Jefferson High School. Okay, so that's our population, all of the wrestlers at Jefferson High School, because that's where we got the random sample from. The random sample was of 30 wrestlers at the school. All right, number 7. In a study conducted in Costa Rica, investigators located and directly approached 46 black iguanas. 2 types of approach strategies were randomly assigned. In one approach strategy, the investigator maintained eye contact with the iguana. In the second approach strategy, the investigator looked away from the iguana while approaching. The response variable measured was the distance of the investigator from the iguana when it decided to run away. Researchers found a significant difference in the mean approach distances for the 2 conditions. Which of the following gives a conclusion that should be made based on the results and provides the best explanation for the conclusion? So if we look at here, it says 2 types of approach strategies were randomly assigned. So we got random assignment. Yep, and then they directly approached. They did this with 46 black iguanas. So there's random assignments, but I do not see where it says random selection here. Hold on. Okay, so here we're just looking at based on the statistical difference. Okay, so they said there's a statistical difference or a significant difference. Okay, so that means if there's a significant difference, that means we can conclude based on the evidence, right? So that means there is significant evidence, right? There is enough evidence to conclude that the difference in the distances, right, was caused. So we want to use the word caused. So there's caused in several of these answers, by the way, because of the random assignment. There's cause and effect. So since there's a significant difference, let's look at the first one. It is not reasonable to conclude that the difference was caused by a different approach strategy because this was not an experiment. No, this is an experiment, and we do have significant difference, so it's not A. It is not reasonable to conclude that the difference was caused by a different approach strategy because there was no control group. No. We actually have random assignment. There's 2 groups, 2 approach strategies, and there's a difference between them. So it is reasonable to assume cause and effect because of random assignment. It's not reasonable to conclude the difference was caused by different strategies because the investigators were not randomly selected. This does not determine whether we can say cause and effect. Remember, random selection, it helps us generalize the results, but it doesn't necessarily preclude us or exclude us from saying cause and effect. So it's not C. It's reasonable to conclude that the difference in mean approach distances was caused. So we got reasonable means significant, statistically significant, and caused by the different approach strategies because of the random assignment. That's correct. Random assignment. Not because of the random selection, because of the random assignment. All right, that's going to do it for the video, guys. Hope you found this useful and informative. As usual, I'll see you in the next one.